Look at your arm right now. There is hair on it. Fine, sparse, almost invisible in most lighting. Now think about the animal you most recently saw at a zoo or in a nature documentary. A chimpanzee, a wolf, a bear, covered from face to foot in a dense coat of fur that your arm hair could not come close to matching. You share roughly 98% of your DNA with a chimpanzee. And yet somewhere in that 2% gap, the instructions for building a thick, warm, protective coat of body hair got quietly switched off. Or did they? The real answer is far stranger than a simple loss, because humans didn't actually lose the ability to grow fur. The genes responsible for dense body hair are still sitting in your genome, largely intact, quietly doing almost nothing. What changed was not the genes. What changed was the instruction set that controls them. And the reason those instructions changed will tell you something about the most defining pressures your species has ever faced. To understand what happened to human body hair, you have to understand what body hair actually does for the animals that have it. The answer is more complex than most people assume. Fur does not simply keep animals warm. It insulates against heat as well as cold, protecting the skin from direct solar radiation. It provides physical protection against abrasion, scratches, and insect bites. In some species, it plays a role in social signaling, in camouflage, and in waterproofing. Fur is a multifunctional biological technology, and losing it carries real costs. For your ancestors to have lost it, something had to make those costs worth paying. The leading explanation, developed most extensively by evolutionary biologist Mark Pagel at the University of Reading and his collaborator Walter Bodmer, is what they call the ectoparasite hypothesis. The argument is straightforward but striking. Dense body hair is an extraordinarily effective habitat for external parasites, lice, ticks, mites, and fleas. These parasites are not merely irritating. They are vectors for serious diseases. In the ancestral environment, where medical treatment did not exist, and even a moderate infection could be fatal, the disease burden carried by ectoparasites living in body hair represented a significant and ongoing threat to survival and reproduction. As hominins began living in larger social groups and spending more time in close physical contact with each other, the transmission of ectoparasites between individuals became more frequent and more dangerous. At some point, the selective pressure began to favor individuals with less dense body hair, because less body hair meant fewer parasites, which meant lower disease burden, which meant higher survival and reproductive rates. Over hundreds of thousands of generations, this pressure steadily reduced the density of body hair across the human lineage. Pagel and Bodmer's hypothesis also predicts something that the evidence confirms, that the loss of body hair should have been accompanied by an enhanced immune system, because a species giving up its first line of physical parasite defense would need a stronger biological defense instead. And human immune systems are, in fact, remarkably sophisticated compared to those of our closest primate relatives. But ectoparasites alone do not tell the whole story. A second major pressure was operating simultaneously, and it may have been even more powerful in shaping the specific pattern of hair loss humans experienced. Your ancestors, at some point in the early Pleistocene, became persistence hunters. Unlike most predators, which rely on speed or ambush, persistence hunting involves tracking prey over long distances at a sustained trot, for hours, sometimes covering 20 or 30 kilometers, until the prey animal overheats and collapses. This hunting strategy, documented in traditional human societies today and analyzed by evolutionary biologist Daniel Lieberman at Harvard University, is only possible because humans are among the very few mammals capable of sweating efficiently enough to thermoregulate during sustained aerobic exercise. Most mammals, including chimpanzees, cool themselves primarily through panting. Panting is highly effective but incompatible with sustained running, because running and panting require the same respiratory muscles and cannot be done simultaneously with full efficiency. Humans evolved a different system. Eccrine sweat glands distributed across nearly the entire body surface, capable of producing extraordinary volumes of sweat that evaporate from the skin and carry heat away with remarkable efficiency. But this sweating system only works if the sweat can reach the skin surface and evaporate. Dense body fur traps sweat against the skin, prevents evaporation, and dramatically reduces the cooling efficiency of the system. For the sweating-based thermoregulation system to work, the fur had to go. This explains something about the specific pattern of human hair loss that the parasite hypothesis alone doesn't fully account for. Humans didn't lose hair uniformly across the body. The top of the head retained thick hair, which protects the brain from direct solar radiation during upright walking in the African sun. The face retained significant hair in adult males, possibly for social signaling functions. The axillary and pubic regions retained hair, possibly because sweat glands in these areas produce different secretions and the hair aids in dispersing pheromone-carrying compounds. What disappeared most dramatically was the dense covering across the trunk and limbs, exactly the regions where the cooling surface area is greatest and where hair retention would most impair thermoregulation during running. The transition from fur to bare skin also required a second adaptation, the dramatic increase in skin pigmentation. Bare skin exposed to equatorial African sunlight is vulnerable to UV radiation in ways that fur-covered skin is not. The evolution of dark skin pigmentation, driven by the protective melanin that absorbs UV rays and prevents DNA damage, was the necessary companion technology to the loss of body hair. Geneticist Nina Jablonski at Pennsylvania State University has spent her career documenting the relationship between UV radiation levels, skin pigmentation, and human migration patterns. Her research shows that dark pigmentation evolved specifically in response to the loss of the fur that had previously protected the skin, and that the variation in human skin color seen across the world today reflects subsequent adaptations as human populations migrated to regions with different UV radiation intensities. But here is the part of the story that most people find genuinely surprising. The genes for dense body hair were not deleted from the human genome. Researcher Alan Packer and his colleagues studying the genetics of human hair follicles have found that the molecular machinery for producing thick terminal hairs, the kind that grow on your head and in your eyebrows, is still present across the body. What changed was the signaling environment that tells those follicles what to produce. Most follicles on the human body were reprogrammed to produce vellus hairs, the fine, nearly invisible hairs you can see on your arm, rather than the terminal hairs they are technically capable of producing. This reprogramming happened primarily through changes in regulatory DNA, the portions of the genome that control when, where, and how strongly genes are expressed, rather than the coding sequences of the genes themselves. These regulatory changes are exactly what evolutionary biologists have come to understand as one of the primary mechanisms of major evolutionary transitions. You don't always need to build new genes. You just need to change the instruction manual for the ones you already have. The implications of this are strange and interesting because those follicles are still there, still capable. The genes are still present. Under specific hormonal conditions, some human follicles will still produce surprisingly thick hairs, which is why certain conditions that alter hormone levels can produce dramatically increased body hair in humans. The underlying machinery never went away. It was just reassigned. What this tells you is something that runs counter to the common mental image of evolution as a process of loss and addition. The human body's transition from fur to bare skin was not primarily a deletion. It was a reprogramming. The capacity for fur remains embedded in your biology. It is just being systematically suppressed, generation after generation, by a set of regulatory instructions that were updated by several 100,000 years of selection pressure in the African heat. You are not an animal that lost its fur. You are an animal whose fur production system was almost entirely redirected by pressures that no longer exist for most of the people alive today, in a world of climate-controlled buildings, synthetic clothing, and medicine that makes ectoparasites a manageable nuisance rather than a lethal threat. The fine hairs on your arm are not the remnants of fur you lost. They are the nearly silenced output of a system that is still technically running, still producing what it was told to produce, still following instructions written in regulatory DNA by a world your ancestors navigated millions of years before you were born. Every so often, in certain light, you can almost see them. And in that moment, you are looking at one of the quietest and most consequential evolutionary decisions your lineage ever made.